All right. Everybody does not have a copy of the notes. Let me hand those out. 2, 3, 4, 5. Yeah. All right. We are going to use the tablets today, or your own PC, Watergems. So if you don't have Watergems on your computer, grab one of the tablets or sit next to someone who does. It's not critical that you have your own computer today. It's mostly, we're just going to take a quick look at the solution to that example that we've worked previously a couple of times. Here. Homework 5 is due on Tuesday, the 18th, so that's our next class meeting. And our exam will be a week after that. Tuesday, February 25th, it'll be in class. We'll have, of course, the 75 minutes of our class period. So generally what I do is I'll have between 4 and 5 questions, depending on the length of the questions. It'll include both concepts and problem solving, so you might expect to have a question where I ask you to explain something, so it could be a short answer. It probably won't be a multiple choice, but we'll talk more about the exam as it gets a little bit closer, you know, in terms of what kind of equation sheet you'll be permitted to use and so on. Today we're going to double check that example we solved last time using Excel. It's the Hardy-Cross example 2. We're going to set that up in Watergems as quick as we can and see if the solution matches. And then we're going to talk about water hammer and surge tanks. And we've got a lot of ground to cover and about 45 minutes remaining. So we're going to really have to rush through the Watergems stuff. I'd like for us to have at least 35 minutes for the water hammer and surge tank. So that'll allow us only about 10 minutes to double check the Watergems example. If you can't get the tablet to work, then maybe just scoot up next to somebody who does have it. Now remember that last time when we finished with the Excel spreadsheet, we were able to know what the flow rate was through each one of these pipes, and we knew the pressure at each of the junctions. And so let's fire up Watergems and see if we can get a similar thing. And I'm just hoping here that Watergems is still installed. It is. All right, so begin Watergems. Now when we draw, it doesn't have to be to scale. So we're just going to draw a schematic of what this pipe network looks like, and then we will put in the pipe characteristics separately while it's loading. Maybe I'll put the pipe characteristics on the board just to make it easier for everybody to copy down. We've got, it looks like this. What's that? A, B, C, D, E. All right, so pipe AF is, AF has a diameter of 0.4. AB has 0.5. BC is 0.65. CD is 0.85. DF 0.5. EC, oh, it's okay. It's already on the lengths and the diameters. Maybe the easiest thing to do then is just to pull open the notes that you had from the previous class so that we can just copy it over. I guess I might as well write EC. EC was 0.6 meters, and then the lengths will be there too. So when we start a new project, then we can just start drawing with the tool that's right over here. It's below the arrow key. This symbol is what we use to start drawing a network. Okay. So the first thing we're going to be putting in are junctions, where, okay, junction, drawing it like this. Escape to stop the pipe, go up, and that. Okay, I'm going to, pardon me?
It is the blue water jet icon,
I don't know that the color so much matters. I'm not sure. My icon, I think, is blue. Yeah. Pull open the junction table, and I'm going to rename my junctions. So junction 1 is A. Junction 6 was the one that I'm calling B. Junction 4 is what I'm calling C. E is junction 5. Junction 2 is F. And junction 3 is D. All right, and the elevations are all constant, so we don't need to change anything for the elevations. I'll need to open up the pipe table and edit both the pipe diameters and the lengths. And so over here on the side, I want it to be user-defined length for all of these so that it's not using the scaled length. I'm going to copy the user-defined length column over, drag it over sideways so it's closer to the diameter. Oh, and I'm in traditional units, and so I should have checked that at the very beginning. I need to go back to Tools, Options, Units, SI, and start over, unfortunately, because I never seem to get it to work very well when I start in different unit systems. So I'll check Tools, Options, Units, SI. All right, good. So starting from scratch, draw. All right, and once again, I'm going to relabel the junctions. This is A, 2 is F, 3 is D, 4 is C, 5 is E, and 6 is B. All right. Now I'm going to open the pipe table and change the diameters. Okay, so label, this is going to be pipe AF, this is pipe DF, CD, CE, EF, AB, BC. And of course I'm recording this. If you can't keep up with the speed that I'm doing it, that's more than fine for you to just go ahead and maybe take a look at it later on. User-defined lengths. Alright, so now I need to double check the lengths and diameters that are given here. The diameter of AF is 500 millimeters. DF is 500. Thanks. 500. CD is 850. CE is 600. EF is, oh, I didn't look at that one. What is it? EF is 700. AB is 500. And BC is 650. So putting in all the diameters, now I need to copy over the lengths. Maybe, I wish I could scroll down and look at the pictures while I type that in maybe. Okay, so the length of AB was 220. Thank you. That'll speed things up. AF is 180. DF 200. Okay. CD 80. CE 50. EF. We already got 220, and then for BC, 100 meters. Okay, the other thing is that all these pipes are made out of, what was the material? Do we remember what the material was for that example? Let's double check. All pipes have a KSub-S of 0.3 millimeters. So we didn't know necessarily what the pipe material is. We'll go into the material table and find something that has a 0.3 millimeters. It might be concrete, KSub-S of, no, 0.3, cast iron. Yeah, there we go. So that'll be 0.3 millimeters. I'll select cast iron. I should do it for all of them. Cast iron. There's probably a way to select all of them simultaneously. Let's see. Can I do that? No. There's probably a way to do it all at once, right? Maybe if I global edit, set, maybe if it was numeric, it would let me type them all in. Cast iron, close. Cast iron. So what else do we need to put in besides the material type, the pipe lengths, the pipe diameters? We wanted to do these calculations using Darcy-Weisbach, which is not the default. So I need to go into calculation options and have it for a steady state solver, go from Hayes and Williams. We want it to be Darcy-Weisbach for the calculation that it does. I also need to define the flow rates. We haven't told it where water comes in and where water comes out. So what I'll need to do to get water to go in is I have to put in a junction that's connected to a reservoir. And so the way to do that is just have off to the side someplace water can come from, and we're going to connect a pipe to that and a pipe to that here. The important thing is that we want to put a known demand of 1.6 cubic meters per second out at E. Okay, so here I've got, if I pull up the nodes, junctions here. For pipe junction E, I want to do a demand collection of, and our flow rate out is 1.6 cubic meters per second, so that's going to be 1,600 liters per second. Liters per second. All right. Now the difficult thing is that it's given that the pressure at A is 600 kPa. So I need to make the reservoir such that the given pressure at A is 600 kPa. And so what that tells me is I'm going to have to choose a reservoir height that gives me a pressure at A of 600 kPa. And the way that you can do that, of course, is that we know that head is pressure divided by gamma. So the height of the water, if I want 600 kPa, then it should be 600 kilonewtons per meter squared divided by 9.81 kilonewtons per meter cubed. And that tells me that the height of the water there, calculator, 600 divided by 9.81, 61.2 meters. So I'll do that, and then I'm going to check to make sure that I have the 600 kPa at A that we're expecting. So 61.2, right? Now it's a little bit tricky because we don't have a certain known pressure at D that's given in the problem statement. So the way that we have to verify the solution is we're going to have to adjust the elevation of this reservoir we've created at D so that it causes a pressure of 567.3 there. And so what I can do is I can say that there's a head of 57.83. So 57.83 is what I'll give for my water elevation here. 57.83 is the known pressure. Okay, let me just double check in the reservoir table to make sure that both of those elevations are given. All right, they are. They were saved. So we've got our demand collection. The water's going to come through these pipes to the reservoir. I want these pipes to be relatively big so that there isn't any head loss through those pipes. And so I'm going to go back into the pipe table and make sure that pipe 8 and pipe 9 are really large so that there's no losses through them. I'll make them 1 meter in diameter, which is extraordinarily big. Any questions so far about how this has been set up or why?
Yeah, when you were doing your head overview,
Uh-huh.
just to get your reservoir elevation.
That I wanted to, yeah, to get the reservoir elevation for junction A and junction D.
And that's the same calculation we made in Excel.
Right.
on your-
Exactly, yeah, that's what we were doing here, where we were relating the head and the pressure. So, go ahead.
Oh, that R times Q to the nth power
Uh-huh.
is the same, will give you the same result as that over there?
No, like to get the head at B, what we did was we knew the head at A was 600 kPa, and so that is 61.162 meters.
Right.
Okay, so to get the head at B, we used that head that we had at A, and then we subtracted the losses, which is calculated by that formula. All right. And then in this check of the solution that we're doing using Watergems, we know the pressure at A and D is due to some water flowing in. And so that's why I had to put reservoir in both of those locations, is because that's where the water is going to come in from in this model.
Just making sure we haven't done water going out yet, right?
No, we actually did. Let me remind you where that was at. When I pulled open junction E, I did a demand collection. So if I go back into the junction table, E has this demand collection of 1,600 liters per second. So that's how I specified that there's flow going out at E. Other questions? All right. So now to get it to execute, we click on the little green button there, compute. Failed. Node is not connected to, oh, it's because I've got this junction just out here doing nothing. Let me delete that and run it again. All right, it's got a solution, and let me have it do some annotation here just so that I can see the solution. I'll do a new annotation that has flow rate. So flow, and I'll offset it 2 and 2. Let's apply it, see where it's at. That's fine. I'm going to turn off the labels. Okay, so let's look at the flow rates that we thought we had in the end. The flow rate through AB, for example, 0.581 was our Q. What does the model say? 547. So there's some differences there. Let's check the pressures to make sure that those were accurate. Junction new annotation, we'll put in pressure. Apply that. Okay, so we've got the 600 kPa there that we are expecting. Down here we should have about 566. It says what we wanted at that D, location D, was 567. So the pressures seem to be lining up, at least in those 2 points. Let's look at pressure at F. According to our model was 553. And this is saying 560. So does anybody know why the pressures that we're seeing are a little bit different and the flow rates are a little bit different? What wasn't taken into account in the pressures that we calculated here when we did this method? The velocity head, right. And so what Watergems, the difference that we're seeing in Watergems, the slight difference in flow rates, and so for example, where we are seeing 547 through BC, in this model we were seeing the flow rate to be, the corrected flow rate to be actually quite a bit different. I'm surprised. I'm wondering if maybe oh yeah, you're absolutely right. I forgot to put that in. So I need to, thanks for noticing that. There is a flow out at B of 600 liters per second. So let me do that. Good catch. So there's a demand collection of 600 liters per second at B. All right. Have I overlooked anything else? Hopefully that brings things closer. There will be some slight differences due to the velocity heads. But now it looks like things are matching up a little bit better. So the handout that we had was saying that BC would be 19 liters per second, and this is saying 13. That's pretty close. EC 644 versus EC 792. EF, we were seeing 800 approximately. Here we're seeing about 900. So, it gets us in the ballpark. The flow rates, I guess the real problem is that if you look at the flow rates, it's taking 1,200 liters per second from here, and we should have 1,200 liters per second coming from this other reservoir, but it's only doing 900. With the reservoirs, we don't have a way to force water into the system quite like we do when we are using an other way, like if we had valves set up or a tank. But so far we've only used reservoirs. But we'll come back to this example when we revisit Watergems for the project, and we'll clean it up a little bit further and get it the rest of the way there.
One more question.
Sure, yeah.
How was you were getting the Watergems to accept flow out from the reservoir?
No, it naturally takes flow out from the reservoir.
So you just put your elevation
Yeah.
and know we can run it?
That's right, yeah. As soon as you define the elevation of the water, then that's where the water will come from if there's an outflow that's defined. Other questions? All right. So like I said, we'll come back to this example later in the semester and see it come a little bit closer to what we solved with the spreadsheet method, because we have to get acquainted with valves, pressure tanks, and so far we've only done reservoirs. But what we're going to continue talking about today, the new material for today's lecture, is related to the speed that shock waves travels through water. That is at the heart of Waterhammer. Let's look at one of these videos on Waterhammer that illustrates the phenomenon we're going to be talking about. All right, so has anybody seen anything like that before or heard of plumbing doing strange things? Let's look at the other video. This one maybe illustrates it even. Oh, that's a shame because that was a good one. All right. Well, the other video, it showed the same thing, somebody with a pounding noise with the plumbing. In the case of that second video, it was someone who was running their dishwasher, and then they walk over towards the water heater, and that's where the sound of the pounding was coming from as they were using the dishwasher, was from the water heater. Now, the phenomenon of Waterhammer, what it has to do with essentially is how quickly valves are being closed. And let me walk you through what causes that pounding sound, and it's more than just an unpleasant sound. It can actually destroy equipment.
Is that the same thing that happens in the old boilers?
It can be, yeah. When you have a reservoir and there's a long pipe, and at the end of that pipe is a valve. Now let's just take a look at the things that are being illustrated here. The total head in the reservoir is just the height of the water, because remember that head is the sum of three things. It's the sum of the velocity head, the pressure head, and the elevation. And so since there's no velocity and no pressure at the top of the water surface in the reservoir, then it's just the water elevation that has to do with the total head that's there. then as water starts to flow through the pipe, then there are head losses, which is why the total head starts to decline. And so you can see that at each of these locations you can find some pressure head. Above that is the velocity head. And if the valve is closed too quickly, then problems can arise. So we start off with water just flowing freely through the pipe, and we're going to just put a control surface around this section of the pipe and look at what happens if the valve is closed too quickly. What will happen in terms of shock waves? If we do a force balance on this element of water, remember that the momentum equation says that there's some imbalance in force if the velocity out is different from the velocity in. And so in steady state flow, when the water's just moving freely through the pipe, the velocity in and the velocity out are the same. And so there isn't going to be any force that arises out of that. But suddenly you close the valve very quickly, say for example. And when you close the valve very quickly, what happens is that the water that's closest to the valve starts slowing down more quickly than the water that's a little bit further away. Remember, water is almost entirely incompressible. Water doesn't compress very easily, but it does compress a little. And that means that when you instantly close a valve, that actually the water that is close to the valve gets sort of squished by the water that's coming from behind it. It's like a pileup on the freeway. If one of the cars stops suddenly, then all the other cars are going to sort of mash up behind it. And so that's what's happened here, is that the water that's close to the valve instantly stops, then the water behind it stops. And these little dashed lines here, what that means is that the pipe begins to swell because there's a higher pressure inside the pipe in this location, because there's more pressure because the water behind it is slowing down suddenly. So there's an imbalance of forces. So the water near the valve stops, but there's momentum that's been going. The water was moving, but then it stopped, and so there's a pressure wave that forms, and it is actually reflected backwards towards the reservoir. And it moves at a speed that's known as celerity. Celerity is the speed of a shock wave moving through water. And this all ties into the fact that water is somewhat compressible, and the pipe is actually elastic. The pipe can expand as the water pressure increases. It swells ever so slightly. And so as it does that, as the pipe expands, it's storing energy. And if the pipe contracts, it's going to release that energy. So there comes a point at which the shock wave has moved its way all the way from the location of the valve back towards the tank. And these little dashed lines, the little dashed lines indicate the fact that the pipe has expanded. The entire pipe is expanded, and there's no flow of water at this point. The water level actually did change in the reservoir. The water level is lower right now than it was initially. So initially the water level was at some height because the total amount of water that's there, the instant that you close the valve, there's some water in the tank and some water in the pipe. But remember that the pipe is expanding slightly because of the shock wave and because of the accumulation of pressure. And as the pipe expands, more water volume can be stored in the pipe. And so some of the water has flowed from the reservoir into the pipe because the pipe got bigger as it expanded. And so there's this delta H that corresponds to the volume of water that was in the reservoir that is now in the tank. I'm sorry, that was in the reservoir that is now in the pipe because the pipe expanded. Because the pipe expanded, it has more energy than it did initially. And in fact, there's more energy in the pipe than there is in the reservoir. So when we had the energy grade line before, you'll notice that the energy grade line is actually going to increase and be greater than the height of the water inside of the tank. And so the water flows backwards from the pipe back into the tank, So initially the water was flowing this way towards the valve, but now the water is flowing the opposite way. Once you get to this point at which there's more energy inside of the pipe than there is in the reservoir. Remember that water always flows from high energy towards low energy. And the reason why it initially was flowing in this top image, it was flowing from the reservoir towards the valve, was that there was more energy in the reservoir than there is at the valve. But that temporarily is sort of turned onto its head if the valve is closed too quickly and there's an accumulation of energy near the valve because of the compressibility of water. So the water flows back into the reservoir, and this shock wave now goes back towards the valve again. C is showing the shock wave's movement, and so it's sort of indicating the speed that the shock wave moves from the reservoir back towards the valve again. And this is a wave of decreased pressure, so that the pipe, instead of expanding, is now starting to contract as the wave goes back towards the valve again. Now the crazy thing is that it can make lots of round trips. It can go back and forth, and there's very little energy loss as the shock wave moves. The movement of a shock wave is different from the movement of water. A little bit of water is moving back and forth each time, just as much as the pipe contracts. And the pipe isn't going to contract and expand that much, just a few percent. And so the total volume of water that's exchanged between the pipe and the reservoir may be, depending on the length of the pipe and its diameter, it could be less than a liter. But in spite of the fact that very little water is being exchanged back and forth, the wave can go back and forth many times, and there isn't much loss in energy as the shock wave is reflected. And so this wave reflection at a speed that's just incredibly fast is what causes the banging that we heard in the first video. It's the sound of the shock wave going back and forth between the valve and the reservoir. And so in most people's homes, the reservoir, in this analogy, is their water heater. And the valve, think of what kind of a valve may be closing quickly. It could be the faucet at the kitchen sink. It could be a machine that is like a dishwasher. Or another example of a valve that's closed really quickly is the refrigerator water dispensers. And the fridge that we have in the copy room used to be in the technician's room. And it actually dispensed water back then. And when you pushed a button and it would dispense water, and then you took your finger off and it would instantly stop. It's not like the valve was slowly closed. It was an instantaneous on-off, and there was a very slight shock wave that you could hear the water hammer moving through the coils in the copper pipe that's in the fridge. So this all ties into how compressible water is. And the definition of compressibility is the change in volume that's occupied by a certain amount of water relative to the change in pressure that's applied to cause that change in volume. And here's a graph of compressibility of water. And you'll notice that it's relatively flat, that the compressibility is not much of a function of the temperature of the water, that whether water is cool or warm does affect the compressibility a little bit, but the units here are in terms of gigapascals. And so the unit change in volume occupied relative to the pressure required, the kilopascals that we're using are several orders of magnitude less than the gigapascals required for a unit change in volume for water. And so at the pressures that we usually see in water systems, water is not very compressible. And the reason why it is slightly compressible is that depending on the pressure that's applied to water, it may take on different formations where each one of these represents a water molecule. And so each red here, for H2O, the red is oxygen, the white balls here are hydrogens. And so it's not that the molecule is changing shape, but how molecules relate to one another, their orientations, water being a very polar molecule, it's going to be attracted to and bond with other water molecules in the liquid form. And so depending on what pressure is applied, it forms different combinations and groupings, and some of these groupings are more efficient and space compact than others. And so water goes through a transition in which formations it's in. So how do you do these calculations? The types of questions that you need to know, types of questions you ask in a water hammer problem is, how big is the shock wave going to be? Like, what's the pressure that you can expect? Because you want to know if the pressure from the water hammer is going to exceed the capacity of the pipe. Another thing that you need to know is, how slowly should I close the valve? And it turns out that if you close the valve more slowly than it takes the water to go through one round trip, then you'll avoid the water hammer. And so it takes a certain amount of time for the water to travel, for the shock wave to go from the valve to the reservoir and back. And if you close the valve slowly enough that that shock wave makes the round trip before the valve is closed, then that will alleviate most of the pressure of the shock wave. But if you close the valve so quickly that the shock wave is going there and comes back and finds that closed valve, then that will result in the largest shock wave and the most pressure accumulating as a result of the event. So to do the calculations, we have to use the bulk modulus of elasticity as one of our parameters, and this is a property of water that is related to its compressibility. It's actually the inverse of compressibility, where in compressibility we were talking about the change in volume relative to a change in pressure. This is the other way around. The bulk modulus of elasticity for water, we have information about how compressible water is at different temperatures and different pressures. And we'll work an example where we have to utilize one of these. But the bulk modulus of elasticity is the specific volume multiplied by the change in pressure that causes a unit change in the volume. So the incremental dV is some change in the specific volume relative to the pressure that's applied. The other thing, the celerity, the speed of the water, is governed by the size of the conduit that the shock wave is traveling through. And so if it's just in infinite space, the water shock wave travels at a different speed than if it's enclosed in a pipe. And so there's the theoretical celerity, which is a function of the density of the fluid and the bulk modulus of elasticity. And so we have a typical speed of about 1440 meters per second for the theoretical celerity. And then there is the celerity of a pressure wave going through a pipe. And you can see that when it's flowing through a pipe, you have to take into account the diameter of the pipe, the material of the pipe itself, the thickness of the pipe walls, and so on. So if you know the speed that the water is traveling and the length of the pipe from the valve to the reservoir, then you can calculate that critical amount of time, the time that you shouldn't close the valve quicker than. And if you've got a really long pipe, that leads to more risk, because the longer the pipe, the more slowly the valve should be closed. Because if it's a long pipe, think that the shock wave can go all the way to the reservoir and come back. You might be able to close the valve quicker than it can make that round trip. And so it's in big municipal water systems that the risk is the greatest, because number one, you're working with large pressures, big diameter pipes, but then also you've got long runs of pipe where closing a valve, some road in a neighborhood, and the shock wave may be going to a reservoir many miles away. So here's how you calculate the pressure increase that happens during a surge. You multiply the density of the fluid by the velocity and the celerity of the speed of the water as it's moving, and that will tell you the maximum increase in pressure. So let's put that into practice, and we'll take a look at the pressure increase that happens from a water hammer. What do you mean multiply it? This calculates the worst case scenario. So if you close the valve slower than the round trip, then the pressure will be less than that. So it's not like you'll get any more than that. It won't like be multiplicative, but this is the worst case scenario. Okay, so we've got some 2,000 foot long pipe made out of steel, and since it's steel, we know the thickness of the pipe and we know the bulk modulus of elasticity for it, and it's carrying water at a known flow rate through a reservoir to a valve. So what we're going to try and find out is what would the pressure increase be if the valve was closed suddenly? It's that worst case scenario. So first of all, we have to know the initial flow velocity before the valve was closed. And before the valve was closed, it was 0.6 cubic feet per second. And the cross-sectional area for this pipe, if it's a 4-inch pipe, then the diameter is 4 divided by 12 feet. And that's the diameter squared times pi divided by 4. That gives us the velocity 6.875 feet per second. That's how fast the water's moving through the pipe before the valve closes. Now, the theoretical celerity, meaning the speed of water, the speed the shock wave can move through water, 320,000 psi times 144 inches squared per square foot, 1.94 slugs per cubic foot. Okay, so the theoretical speed of the water is 4874 feet per second. And the speed of the shock wave through a pipe is going to be less than that, though. It's going to be attenuated by the pipe material properties. And so what is the lower speed of the shock wave moving through the pipe? We have to calculate the c. So it'll be the square root of the theoretical celerity, 4874 feet per second, that quantity squared. And now 1 plus E sub v, so that's the pipe material of 320,000 pounds per inch squared times 144 inches squared per foot squared. And then we multiply that by the diameter, which is 4/12 of a foot. And the thickness of the pipe, 0.01667 feet, is how thick this pipe is, because we know the thickness is 0.2 inches. I've converted that into feet to get the thickness of the pipe. And now we have to multiply it by the 28 times 10 to the 6th pounds per square inch, which is the pipe property. This is the E sub p value for the pipe, bulk modulus elasticity for the pipe, and convert it from inches squared to feet squared times 144 inches squared per feet squared. All right. And all of that is in the square root. So we do the calculations and get that it's 4397 feet per second through the pipe. That's how quickly the shock wave moves through this particular pipe. For the temperature that we've got, for the thickness of that pipe, for what it's made out of, that's how quickly the shock wave moves through this pipe. And so the maximum increase in pressure that we could potentially see, the delta P, is going to be the density times the celerity times the initial velocity. So the density of water is 1.94 slugs per cubic foot. The celerity is 4397 feet per second. And the initial velocity that we'd already calculated is 6.875 feet per second. Okay, so that tells us that the maximum pressure increase because of the shock wave is going to be 58,649 pounds of force per square foot, which if you divide that by 144, that is 407 psi. That's about 2,800 kPa. The maximum allowable pressure on most water heaters is in the range of about 900 kPa. And so if a shock wave came through the system that big, then it would cause most people's water heaters to fail. That's usually the appliance in people's homes that fails the quickest, is the water heater. Yeah.
What is
The thickness of the pipe.
okay.
Yeah. Other questions? Okay, so that's all about the increase in pressure. Now, how long does it take for that shock wave to make the round trip? At that speed that we'd calculated already, the time is going to be twice the travel distance. And so if the length is 2,000 feet, it's going to have to make a round trip. It'll go from the valve to the reservoir and back again. So it'll be 4,000 feet. And then it's moving at a speed of 4397 feet per second. So that's 0.91 seconds. So think about how quickly you can close a valve. Some valves close slowly, like a gate valve is slowly going down into the flow, and it probably wouldn't close all the way from open to close in under a second. But a ball valve could, potentially. So this tells you how you could avoid that maximum pressure. There's still going to be an increase in pressure no matter how slowly you close it. It may not be measurable. But one way to avoid water hammer is to have automated systems that close a valve, like with a machine using an electric motor to control the speed that the valve is closed. Another way to do it is with a surge tank. And what a surge tank would do is it would provide a place that extra pressure could be relieved by allowing the water level to increase in the surge tank. So if we wanted to have a surge tank, the question would be is how large should this surge tank be for the case that we've just described? If we've got this 2,000 foot long pipe with a 4-inch diameter and we know the flow velocity, the way that you can size a surge tank, the equation is shown here to tell you the maximum surge depth that can be expected. And if we were going to use a surge depth that's only allowed to be 1 foot, then we'd maybe want to know how big should the surge tank be in terms of its diameter that's required. And so for this, we can rearrange the equation, which initially is meant for finding the maximum surge depth that you'll see. We can rearrange that to be that S max divided by V naught squared is AL, area of the tank, times G. And then that goes to the area of the tank should be the area of the pipe, the length of the pipe, S max, allowable depth, initial velocity V naught squared times G. So if we have a pipe diameter of 4 inches like we do in this problem, the area of the pipe is 0.08727 feet. And so we can substitute in the area of the pipe, 0.08727 square feet. The length of the pipe is 2,000 square feet. And then the maximum depth we want to see in the surge tank is 1 foot. And we know that the initial velocity was 6.875 feet per second. And that's squared, and G is 32.2 feet per second squared. Then the area of the tank its cross-sectional area should be 256.2 square feet. And so if we do that, the diameter is 4 times the area divided by pi. That's just rearranging the formula for area being pi d squared divided by 4. Then we'll get 18.06 feet. That is a large diameter tank. So probably we'd want to redesign it so that the allowable surge depth is greater than 1 foot. But the idea of this device is just for a place to relieve the shock wave, because remember, the water is going to be moving in and out of the pipe as the pipe expands. And that's what this formula is really looking at, is how much extra water is there as a result of the shock wave. I'm sorry that we've gone over time today. It looks like I took 2 additional minutes, so I'll be sure to refund that in a future lecture so I don't take up too much of your time. Let's take one final look at the announcements here. Remember that you've got a homework due on Tuesday. It includes some water hammer stuff, so if you've got any questions as you work through that, please feel free to come see me during my office hours or anytime I'm in.